now we'll come back to the concept of work again. Let F be a constant force applied to an object that produces a displacement d. If the angle between F and D is theta, then the work done by the force is F dot D, which is just the magnitude of F times the magnitude of D times cosine of theta. So we have a force F that's acting on an object in a certain direction that makes an angle theta with the direction of motion. To calculate the work done, we're finding that magnitude of F times magnitude of D cosine theta, which, remember, this length of this vector is the magnitude of F times cosine of theta. That is the projection, the length of the projection of F onto theta. So that would be the amount of the force F that's going in the direction of motion. So that times the vector D would give you the work. Okay, so again, we're just taking the force in the direction of motion times the distance that the object travels. So if you want to work with it with vectors, just do F dot D. So let's say we have a force F given by 3, 3, 2. So you can represent that. The tail of it's at the origin and the tip of it is at the point 3, 3, 2 in 3 space. Now the object is being moved from the point 1, 1, 0 to the point 6, 6, 0. So that's our displacement vector. So if I want to use the F dot D to calculate the work, I have my force is 3, 3, 2. The displacement vector is just the vector between 1, 1, 0 and 6, 6, 0, which will be 6 minus 1, 6 minus 1, 0 minus 0. Just find the position vector from P to Q. So now we just need the dot product of the force with this displacement vector to be 15 plus 15 plus 0. Notice that work is a scalar. Now, because work is the magnitude of F times the magnitude of D times cosine of theta, if the angle theta is 90 degrees, in other words, if the force applied is perpendicular to the direction of movement, there will be no work done. The work will be equal to 0 since the cosine of 90 degrees is equal to 0. Okay, now let's look at another situation. Often projections are used to express a force in terms of its orthogonal components. So in this problem, we have a force, gravitational force, that's acting on that box on the ramp and it's pulling it straight down. What we want to do is to be able to take that force and break it into two components. One component will be parallel to that ramp, and the other one is going to be orthogonal to it, or normal to that vector down the plane. So this is our parallel component of F, and this is our normal component of F. Okay. Now the two things going on here is we have the projection of the force in the direction that's parallel. That one determines the tendency of the object to slide down the plane. So if you want to try to hold the box in place, you have to figure out the amount of that force that's tending to pull that object down the plane. Now also, this normal force is giving you the it's giving you the tendency of the object to stick to the plane. So you've got these two components, the parallel one that's making it come down the plane, and the normal one is the one that's making it stick to the plane. So let's see how we can use that. We have a 10-pound block resting on the plane, and the plane's inclined at 30 degrees below the horizontal. We want the components of the gravitational force that are parallel and normal to the plane. Well, the gravitational force is this vector, is represented by this vector F. Since the weight of that block is 10 pounds, look at that vector. If we have it pulling straight down, then a representation for that vector, if you put that on the coordinate system, we'd need to find that point where that arrow ended. Because the length of that needs to be 10, which is representing the weight, this point would be the point 0, negative 10. So if we're representing that vector, it would be 0, negative 10. Because 0, negative 10 is where that point, the tip of that vector, would end. Now you could also do it by figuring out what that angle is made with the positive x-axis. And remember, you can take the magnitude, 10, times cosine of the angle, which is 270, plus the sine of 270. J, which would end up being 10 times cosine of 270 is 0, and sine of 270 is negative 1. So we have negative 10j, which could also be represented as 0, negative 10 in component form. Okay, so now, if we're trying to find the component of this vector F that's actually parallel to that plane, what we want to do then is we want to project that force F onto the plane. So we need a vector that's representing a vector in that direction that the plane is slanting. To do that, we don't really care how long that vector is because we're going to be projecting F onto it, and that projection is what determines the length of the vector that's parallel. But what we want to do is just to get a vector that's going in that same direction. Now the way to do that would be looking at a horizontal here. Assume this is your x-axis. If this ramp is at an inclination of 30 degrees here, that means that this angle here is also 30 degrees. And we can call this angle negative 30 degrees since it's below the x-axis. So if I want to find a vector going down the plane, I'm going to assume that it just has length 1. So that vector v, which is representing the slope of that plane, would be 1 times cosine of negative 30 I plus 1 times sine of negative 30 j. Now cosine of negative 30 is the same thing as cosine of 30, which is the square root of 3 over 2. And sine of negative 30 is a negative sine of 30, which is 1/2. So this vector v would be the square root of 3 over 2, negative 1/2 in component form. So now I want to project F onto v. That will give me this vector that's going in the same direction as v, which is coinciding with the ramp, but it's going to be the length of that projection. So the projection of F onto v will be F dot v over v dot v times the vector v. F dot v will be 0 plus 5. V dot v will be 3/4 plus 1/4 which is just 1. Now remember, v dot v is the same thing as the magnitude of v squared. We created v having magnitude 1. So of course that's just going to be 1, which is what we have for the denominator. Now the vector v. So we have 5 times square root of 3 over 2, negative 1/2. Now that is the vector represented going downward on this ramp. So that is our parallel vector. I'll call it P. Now we want to find the vector N, which is in this other direction. It needs to be perpendicular to P. Now notice that F is equal to N plus P. Remember how you add two vectors. That means if we're looking for N will just be F minus P, which is 0, negative 10, minus 5 times the square root of 3 over 2, negative 5/2. Negative 5 times the square root of 3 over 2, and then negative 10, which is negative 20/2, plus 5/2, which will be negative 15/2. And if you want to check, P dot N needs to be 0 because they're supposed to be orthogonal. So if we did P dot N, we would have, let's see, 25 times 3 over 4, and it's going to be negative, and then plus 75 over 4, which is 0. So P is orthogonal to N.